Let's face it, relativity is confusing. What little physics of relativity peers out into popular culture through films like Interstellar show the warping of space and time, but they never tackle how this actually happens. And when you try to learn more on your own, you find diagrams like this, which are not helpful. In this video, I will compare the mind-bending geometry of special relativity to the space we're familiar with, covering these key concepts along the way. In doing so, I hope to shed a little more light on how relativity differs from our everyday world, and how this affects the nature of causality itself. Before we get to special relativity, it's easier to begin with an analogy to help us get a feel for what we even mean by relativity. Let's imagine that we have two surveyors who both need to survey the same tract of land, specifically at point A, shown here. One surveyor works during the day, and they get their directions of north and east from a magnetic compass. Their coordinates are shown in yellow. The second surveyor is a night owl, and they measure north and east by Polaris, the North Star, thereby using Earth's axis of rotation. Their coordinates are shown in purple. Note that the two axes our surveyors chose are based on different observations of north, which don't exactly agree. Neither surveyor is wrong for their choice of axes. North and east are only convenient directions by which to create a grid from, so there's no reason to use one axis over the other. The two surveyors get along well enough, despite their sleep schedule differences. That is, until they discover that they have a discrepancy in their surveyor's logs. Point A appears at different coordinates for the two surveyors. But how can this be? The point is clearly the same, but the two surveyors can't agree on where it is. Is there some more objective measure of the point than its respective north and eastward location? It turns out that there is. While the point's coordinates on each axis are different between the two surveyors, the direct distance to the point remains the same for both. Mathematically, we know this based on the Pythagorean theorem. The side lengths A and B can change without affecting the length of the hypotenuse D. Even though the two surveyors found different measurements for the location of the point, the distance to the point remains the same for both. Now, what does this have to do with relativity? To get there, we'll have to make a few adjustments to our surveyor scene. First, we adjust our axes. While the surveyors worked with north and eastward spatial dimensions, in special relativity we have space-time, where now one of our axes becomes time. Instead of a location in a particular place, we will instead refer to an event. An event is something that occurs at a particular place at a particular time, such as a firecracker going off or a bell being rung. So, for an event, moving left or right represents motion through space. Moving up shows events further in the future, and moving down shows events further in the past. Events happening on the same horizontal line are said to be simultaneous, essentially in the present. What we have now is called a space-time diagram. Thus, one can imagine that as time moves forward, this is visible by moving upwards on the graph. Objects which appear still will carve out a straight vertical line, as they make no progress through space, either left or right. If an object is moving, then it carves out a diagonal line as it moves over by some distance. Objects moving slowly will have a steeper path than objects moving fast, as they traverse less distance for every unit of time. Now that we have the framework, let's tie it together. What is the geometry of the space around us? Now, as we discussed before, in regular space, the distance between 2 points is determined through the Pythagorean theorem. A squared plus b squared equals d squared. If we trace a line of constant distance around a given point, what we get is shown here, a circle. Just as before, when the second surveyor's axes were tilted, all the points along the circle could be seen as the same point in space in a rotating reference frame. This is a fundamental aspect of what is called Euclidean geometry. In Euclidean geometry, the angles in a triangle add up to 180 degrees. 3 left turns can bring you back to where you started, and the shortest distance between 2 points is a straight line. These examples sound obvious, but they are a consequence of the type of universe we live in. So this brings us to the question, what is the geometry of space-time? Just as the distance between 2 points remains the same in space, it turns out that the distance between 2 events remains the same in space-time. This distance in spacetime is called the interval, I, and this is known as the invariance of the interval. It turns out that the equation for the interval in spacetime does not play by the same rules as classical Euclidean geometry. What we have now is Lorentzian geometry. Instead of the square of the distance being the sum of the squares, the square of the interval is the difference of the squares, and that sign change makes a big difference. So, if a line of constant distance in Euclidean geometry traces a circle, then what shape will a line of constant distance trace in Lorentzian geometry? Since the distance to a point involves subtraction, increasing the distance separation means you have to increase the time separation to keep the result equal, and vice versa. Thus, rather than our points of equal distance tracing out a circle, they instead form a hyperbola. This is difficult to wrap one's mind around. How can each of those points be the same distance away? They're clearly not, judging by the graph. This is misleading, however, because the graph and your screen are displaying a Euclidean representation of Lorentzian space. The points on your screen measure distance based on addition, not subtraction, and so you just have to imagine that each of the points are actually the same distance away. In this geometry, we can't actually visualize. Fun stuff. The next question you might be wondering is, now that we have all these events on this curve that are the same distance away, what does that mean? What is equal distance in spacetime? Each point on the hyperbola is the same event, but observed from a new reference frame determined by its relative speed. This speed is denoted as a fraction of the speed of light from 0 to 1, where 0 is stationary, 0.5 is 50% light speed, and so on. This might be easier to visualize if I put in new coordinates, corresponding to the coordinates in a reference frame moving at some constant speed relative to us. This is the equivalent in the surveyor analogy of the tilted axes of the second surveyor. Now, when we see the event's position distort, it is clear why. It's not the event that's changing, but the coordinate frame itself. The event is always at the same point in each new reference frame. This stretching of the reference frame due to velocity is called a Lorentz transformation. These lines of constant distance get even more interesting and beautiful if I include more points spaced equidistant apart on the x and y axes. You can see that when the reference frame changes, each follows a hyperbolic curve, and although they spread apart, they remain lined up along their axes. It looks like the original axes have been twisted, and this is no coincidence. Just as circles in Euclidean geometry trace constant distance while rotating, hyperbolas trace constant distance through the rotation of a Lorentz transformation. You might also notice that no curve ever seems to quite reach the two white dashed diagonal lines. If you recall, a diagonal line represents a constant speed, and in this case, that speed is the speed of light. This is the manifestation of the speed of light as the universe's speed limit. This is evident through the difference between the red and blue hyperbolas. Events along the red hyperbolas are separated from the origin by more time than space, whereas the blue hyperbolas are separated by more space than time. This is the difference between space-like and time-like intervals. Time-like intervals are causally connected. You can reach future events along time-like intervals by traveling at a speed lower than the speed of light. In contrast, space-like intervals require speeds faster than light to reach, making these points causally disconnected from the origin. Now, this has some bizarre consequences for what we observe about an object traveling at different relative speeds. Before I show these, though, it's important to keep in mind what I mean by observing something. When we're talking about observing something, we're referring to the fixed coordinate axes. The horizontal line represents the present space around us, and the vertical line represents the past and future of that space. Combined, these form the stationary frame of reference around us, which does not change. Now for some examples. Say I have a metal rod whose length is 4 units long, represented by points A and B. If this metal rod travels at 80% the speed of light, you can see from the red line's intersection at t equals 0, the moment where we measure its length, that the rod has gotten shorter. Compare this to its original length, highlighted by the blue lines. This is the phenomenon of length contraction. Objects traveling at high speeds become observably, literally shorter along their direction of travel. Instead of a rod, let's say we have a clock which ticks at a uniform speed, represented by points A and B, set 2 seconds apart. As before, we'll compare the duration between ticks by the red and blue lines' intersection with the y-axis. When the clock travels at 80% the speed of light, it's clear that the time between ticks not only arrives sooner, but is also shorter in duration, now taking only 1.5 seconds, i.e., from our perspective, the clock is running fast. This is called time dilation, and its effects are made clear through its portrayal in the movie Interstellar. Now here's where it gets really weird. Instead of a rod of some length, say we have 3 events which take place at the same time from our frame of reference. Maybe they're synchronized fireworks at a concert. If we change the velocity of their reference frame relative to us, it becomes clear that the timing of the events change. Event A happens first, then B, then C. This phenomenon is the relativity of simultaneity, and this contradicts our most basic assumptions about how events relate to each other in our world. In fact, as you can see from the distorted x-axis, you can theoretically find some reference frame where the past of another reference frame is your present. There is a reference frame where my present is the same as that of ancient Rome at some exact place and time, which is the intersection of the 2 present lines. How can this happen? Does relativity of simultaneity throw all logic out the window? Well, no. Events A, B, and C are separated by more space than time, and therefore have space-like separation. This means that they are causally disconnected from each other, and the timing of the events cannot have any impact on causality. Likewise, I can never reach that point in space where my present is in ancient Rome, as I would have to travel faster than light. Alright, for the sake of argument, what happens if we travel at the speed of light? Although it's not physically possible, here is the corresponding change in the diagram. You can see that the graph seems to have completely flattened itself along that diagonal line. The speed of light is not a valid reference frame at all. There is no separation between distances or times, just some sort of infinitely dense smush of both. Sometimes, people will argue that this means that light is everywhere at once, or that light has no sense of time. But, more accurately, considering the speed of light as the reference frame is like dividing by 0 in math. It's nonsensical and can't be defined or described in any meaningful way. Since light itself is a propagating effect, this is fine. It didn't need a reference frame anyway. So, there you have it, the confusing world of relativity. Thanks for making it to the end of the video. I hope this geometry makes a little more sense now, and even if you can't visualize it, at least you have an idea of how space-time behaves compared to the space we're normally familiar with. I would appreciate a like if you enjoyed the video. In this intro, I didn't have time to cover more aspects of relativity, such as the twins paradox or light cones, but I hope this encourages you to learn more of the physics on your own. So with that, thanks for watching.